So as I said, I'm Carlos Moro. I'm an assistant professor at Texas State University. But this work also has been done with the help of my former advisor, Professor Belay, and also we're also very happy to announce the new Professor Francioso that got a position in California. So that reflects the good work that we have been doing in Purdue, and we are continuing it in Texas State University with our new generation. So first I'm going to start with a background and introduction that Larry did a very good job explaining everything, but I'm going to touch a few points. Then I'm going to explain the procedure that we follow. We are going to show the results, the findings, and also make some takeaways, some conclusions of this study. So as we all know, not only in this session, in the whole convention, everyone is speaking about this, speaking about CO2 emissions. CO2 emissions are not going to stop because we are building more and more every day. So since the 19th century, the 20th century, the CO2 emissions are increasing, and even in the last 50 years, they are rebounding so high. Indeed, we have the highest level in the last 3-5 million years, and I don't say that. Environmental Protect Agency basically declares that. And this is causing a lot of things, a lot of problems, global warming, climate change, also air pollution, this pollution that we're having not only in the atmosphere but also in the cities is producing more than 4 million deaths, premature deaths per year that we can prevent. And as I said, this is not expected to decrease because the population base is increasing every single day, so we are expecting to have more impacts if we continue along these lines. So the United Nations basically have these 17 goals, sustainable goals, and if you think about it, more than 40% are completely related to sustainability. That doesn't mean that I want to argue that this is sustainable. That means that they are basically saying we need to do this, and this is a problem. That means that this is a top priority in our world, and we need to do something about it. How can we do about it? As you all know in this room, concrete is based on all these materials, and one of them is the most responsible one for the CO2 emissions, that is the cement paste. That is the cement, in this case, because of the carbon calcination process and also using of the fossil fuels. Anyways, concrete is a really good material, and as also some speakers were mentioning, is the second most used, only after the water. But if you think about it, we use a lot of water in concrete, so actually we can claim that it's the first one used. But we always have, or we have a material that not only emits CO2 but also absorbs CO2. Indeed, there is a study that basically analyzed that 43% of the CO2 emitted only for concrete in 70 years was reclaimed by the concrete itself. That means that we don't have to do anything about it. It was uptake naturally. And in order to analyze different CO2 capture in concrete, there are two main methods that are being used. One is the passive, that is the actual natural carbonation that happens every single year. It's a really slow process. So the other way, in order to accelerate this, because we cannot wait 40 years, is, sorry, it's a bit a mess, but is the active carbonation. That means that we are promoting this CO2 capture, especially at an early age. And the good thing about this is this is not only increasing the CO2 capture, but also is improving other properties, like, for example, compressive strength, durability, and other things in the long term. From the main, or the main hydration process, the A light and the B light, normally in the passive carbonation, the calcium hydroxide is the one that is going to carbonate first. Then also calcium silicate hydrate can carbonate. But the good thing is, with this active carbonation, we are going one step further. What I mean is we don't go directly to produce CSH and then CH and then carbonate the CH. We can go directly from A light and B light to CSH for basically eliminating CH that is a compound is a byproduct of the reactions that can react with chlorides and can have also damage on concrete like in the long term, especially for durability. So we use, this session is about nanotechnology, right? So we use nanotitanium dioxide to do that. And this product has been used like for porosity reduction, the filling effect, also nucleation effect because of the size of the nanoparticles. It also is known for restrict the CH size. That means that it's becoming more and more reactive because the surface area is increasing compared to its overall volume, and also is known for improving the durability. Also, a lot of different studies show that the compressive strength is increasing while adding a small percentage of this product, but and also has like some photocatalytic properties that are being used like in pavements and other things. That means that it not only has one benefit, it has multiple benefits. Okay? But also in one of our former studies, we saw that here I show the phenolphthalein test with different recycle aggregates. That means M0 means no, only unnatural aggregate. M50 means 50 recycle aggregate, 50 natural aggregate, and M100 means like all recycled concrete aggregate with different percentage of nanotitanium dioxide. And we can, in this test, we can clearly see that the carbonation is increasing with the use of recycled concrete aggregate, that is a well-known thing, but also with the use of nanotitanium dioxide. That means that maybe this is suggesting that like nanotitanium dioxide can promote the CO2 capture. And the reason is, why is that? So our first hypothesis is because of the restriction of this CSH. If the nanotitanium dioxide reduces the size of the CH, as I said, it becomes more reactive. If it becomes more reactive, probably it's going to be easier for it to be carbonated during the CO2 exposure. So in order to test this hypothesis, we did like 4 different mortars, 4 different cement pastes, sorry, with 4% of nanotitanium dioxide from 0 to 2%. We first like cured the molds only for 12 hours, and then we pre-cure them for 12 more hours because if we before tested like just removing from the molds and put it in the carbonation chamber, and the humidity was so high that the efficiency in the CO2 capture was not that much. So we decided like to do a pre-curing with a 50% like as a preconditioning in order to improve the efficiency of this CO2 capture. Then we did 2 different groups, basically. I put pre-curing, but it's basically conventional curing, that we stay in the same curing room. And then we put like a group in the CO2 curing chamber with a 20% CO2 concentration for 12 hours. And then we move again like the CO2 cure samples to the same chamber, and we tested compressive strength and then TGA and XRD to explore further the microstructure of this analysis. If I show here compressive strength with the 2 different curing methods, compressive strength on the y-axis and then percentage of nanotitanium dioxide on the y-axis, and if we follow the blue line, that is the normal curing or moist curing or the conventional curing, we can see that the increasing the percentage of nanotitanium dioxide is beneficial to improve the compressive strength, right? We already saw that in the literature, but the interesting part is like if we did the compressive strength in the CO2 cure samples, the optimal percentage of nanotitanium dioxide is lower, right? Like now, the maximum value that we have is 0.5%. And so like the question is, why is lower than in normal cure sample? Our hypothesis on that is that the porosity reduction that happens during the CO2 capture basically blocks the beneficial effects that these nanomaterials could have because of the dual porosity reduction happening because of the nanoparticles, but also for the CO2 carbonation during the chamber. Okay? Then also, in order to further explore that, we did like some TGA analysis to quantify the CO2 capture and XRD analysis. For the TGA, we first analyze the non-exposed sample, and we can calculate the calcium carbonate content that basically happens in this region right here after like 550 until like 750 more or less. And also we quantify the same calcium carbonate in the exposed sample. So basically we are subtracting the calcium carbonate content from the exposed sample minus the non-exposed sample. So in that case we can see the CO2 capture that was taken during the CO2 curing. And we use like different, like the first derivative and the second derivative to be like more precise on this. Like what I mean is like we didn't use strictly 550. It was different in every single sample because the TGA basically has different shapes. And basically we can then multiply to obtain the CO2 capture on all these based, as I said, like in the exposed minus the non-exposed sample. And the results show that the increasing of titanium dioxide percentage also increase the CO2 capture. That means that like it's going up and up, even though the compressive strength didn't increase that much. Okay? These are for TGA results. Then we also did that for XRD. We did XRD analysis for all these samples from 0, 0.5%, 1%, and 2%, and we did the Rydberg quantification. That means quantitative XRD, and we quantify all the different phases that in these samples we could get the crystalline phases. And we saw that not only the CO2 curing promotes the carbonation of belite, because in our samples CO2 cure, like basically our percentage of belite is almost half. But also if we add higher amounts, the highest amounts in this study, 1 and 2% of nanotitanium dioxide, this carbonation of belite is even further increased. And we are basically using all the belite remaining in the samples, and we are basically producing CSH on that. That's a good sign because also this belite is very slow reactive. That means that we are accelerating the whole process to further improve the properties. But this session is about decarbonation. Okay? Right now I only spoke about effects of the nanoparticles, but how is this related to the global warming potential? So the global warming potential, there are like two key things that we need to consider. One, Larry already mentioned, that is the system boundary, right? If you stop from A1 to A3, it's not the same than going from A1 to D, right? But also the second one is using is defining what the functional unit is. Functional unit is basically the unit that you are going to use to compare the samples. You can compare the samples only by volume, but also volume properties, also volume property, compressive strength and durability, and so on, so on, so on. So we wanted to see how the nanoparticles basically change the global warming potential depending on the functional unit that we use. So here in this graph, I show the functional unit 1 that is basically defined as only the volume, and is like the same for the normal curing and the carbonated curing, because we only use the mixed proportioning. And we can see that the nanoparticles increase the global warming potential because the production of nanotitanium dioxide is emits a lot of CO2. But if we use other functional units like volume and compressive strength, for example, for the normal cure, we can see that the nanoparticles actually decrease the CO2 emissions or the global warming potential associated with that. Why? Because it improves the compressive strength, right? So we can lower the amount of cement that we are using, and indeed, instead of having a bad effect in the environment, we'll have a good effect because of the lower cement content that we need to use. We also calculate the functional unit 2, that means volume plus compressive strength, of the CO2 cure samples. And this is further improved because of the increase in compressive strength that happens during the carbonation process, during the CO2 curing process. And in that case, a small amount of nanoparticles still decrease the global warming potential compared to the reference sample, but if you add a 2%, right now is not good for decreasing the global warming potential, right? Like the net CO2 emissions. In this case, I only use compressive strength, but what if we add also the CO2 capture? If we use the CO2 capture, we can see that the global warming potential or the net CO2 emissions of all the samples with a nanoparticle show lower amount than the sample with no nanoparticles, but also not only this small reduction that you can see there, and you can see, okay, it's not that beneficial, but it's not only that, because you actually will need to compare the red dots with the blue dots that you have on top. So we are having a reduction from like 1,040 more or less to like 830. So we are basically doing a 20% only with 0.5% of nanoparticles, right? So it's a huge amount that we are reducing. So our conclusions for this study were that the nanotitanium addition increases the CO2 uptake during the CO2 curing, that this addition also promotes the carbonation of B-light, especially in samples with CO2 cure samples, and that the use of nanotitanium dioxide may decrease the net CO2 emissions, but we need to consider that in the unit that we are using. So like the functional unit that we decide to use should be one that basically contains not only the volume but also properties of the sample, like compressive strength and promotion of CO2 uptake. And we know that these nanoparticles also have positive effects during the durability, so this can be further improved if we consider durability as well. And now I'm very happy, well, these are the references that I use, and then I'm going to be very happy to answer all the questions if you have any.